Hello, my name is Lobo, and I'm a fifth-year co-op student from McMaster. However, I'm working at Simon Fraser for the past 6 months doing co-op in the Dodge group. And what I've been doing over the past 6 months is calibrating a new experiment called the visible probe spectrometer. And to calibrate the experiment, we used a test case of noble metals gold and copper. So I'd like to start off with talking about the motivation for our research. Then I'll go into talking about what the visible probe spectrometer is and how it works. Then I'll show you guys our experiment setup, two-temperature model, which we use to compare our experimental results with theory. And then I'll show some results in comparison to the simulation results. And then I'll go on to talk about future work. So our motivation for our research is to better understand how hot electrons equilibrate in materials. And we can achieve this by using femtosecond time resolution, because the equilibration process takes on several picoseconds to complete. We also like to know how the equilibration process depends on photon energy and the total energy. And this is also, we also have the ability to do this in our experiment, because we can tune both the pump and the probe wavelengths over a wide range of photon energies, wavelengths ranging from 420 nanometers up to 3,000 nanometers. And the ultimate goal of our research is to better understand quantum materials and correlated electron systems. So the visible probe spectrometer works by using two femtosecond pulse lasers targeted at the same point on the sample. The pump laser is used to impart energy directly to the electrons, creating a non-equilibrium-like state. And the probe beam is reflected and captured by a photodetector. And the photodetector measures the differential reflectivity signal, delta R over R. So, and the differential reflectivity signal is linearly related to the change in electron temperature for electron temperatures below 3,000 degrees Kelvin. So what we can do is we can parse over the time domain of the equilibration process by adjusting the relative overlap of the two pulses with respect to an automated delay stage. So what we can learn from this experiment are two key factors of the equilibration process, which is the electron-photon coupling factor, G, which covers the rate at which electrons convert their thermal energy into phonons into the lattice. And this is somewhat difficult to measure by other experiments. So pump probe spectroscopy is very useful in that sense. Another parameter we can get out of our experiment is the equilibrium thermal conductivity, which governs the rate at which thermal electrons diffuse throughout a material. So here's a schematic of our experiment setup. And at the bottom, we start off with two optical parametric amplifiers, which use frequency doubling techniques and nonlinear optics to convert this 800 nanometer titanium sapphire pulse laser into a wide range of output frequencies. So following the pump OPA, it goes through, with a repetition rate of 1 kilohertz, it goes through a 500 hertz beam chopper, which takes out exactly half of the pulses. And these missing pulses are used as a reference signal. The pump then goes through a half-wave plate and polarizer, which allows us to adjust the intensity of the beam, and then goes through a pinhole aperture and focusing lens, which limits the beam width to approximately 1 millimeter over the entire spectral range. Part of the beam is picked up by a reference photodiode, and a large portion is incident onto the sample, creating the non-equilibrium states. The probe beam is sent through an automated delay stage, and it's reflected off the same point on the sample and picked up by a probe photodiode. Both signals are sent to the boxcar amplifier, which gates and averages the pulses. So as I said earlier, every other pulse is not pumped and is used as a reference signal. We can take time-resolved measurements by modifying the path length of the probe beam with respect to the pump through an automated delay stage. At each path length, we measure over 50 pulses and average the data. And the transient reflectivity signal is taken for a wide range of pump photon energies and pump powers. So over here we have some sample data for optimal conditions on polycrystalline gold at 608 nanometer pump and a 486 nanometer probe. The differential reflectivity reflectivity signal is shown on the y-axis as a function of time for a wide range of pump powers. And as you can see, the equilibration process is completed within 4 to 8 picoseconds, depending on the total power of the beam. On the bottom left, we show the same plot on a semi-logarithmic scale, and the dotted lines are applied exponential fits plus a constant. The graphs are not perfectly linear because there is a background signal which skews that. On the right, we have a blow up of the peak change in electron temperature or reflectivity signal, and you can see that we started our fits roughly 1 picosecond after the peak electron temperature because we want the hot thermal gas to thermalize within itself, so we can understand. So now I'd like to talk about the two-temperature model, which is a coupled differential equation that describes the temperature evolution of the electron and lattice temperatures, the time evolution of electron and lattice temperatures, and it's given by this coupled partial differential equation in time and position. The first term in equation 1 is the diffusion term. The second term is the electron-photon coupling term. And the third term, S, is the rate at which energy is transferred from the pulse directly to the electrons. So solving these simulations numerically, we get results like these for electron and lattice temperature profiles. And one thing to note is that change in electron temperature varies on the order of 1,000 degrees Kelvin, whereas the lattice temperature changes by roughly 5 degrees Kelvin. And this is due to the large difference in heat capacities between the two. Looking at the top right graph, which shows the surface temperature profile of the electrons, you can see that the transient signal looks much like the differential reflectivity signal. And again, this is because the differential reflectivity and the change in electron temperature are linearly related. So once again, we apply exponential fits to these transient temperature signals and extract the decay rate, much like we did with the experiment data. And we plot them together on a graph. So here are results for gold. The markers indicate experiment data for a range of pump wavelengths. The y-axis is the decay rate, and the x-axis is the peak change in electron temperature. Varying values of G and K, in our model, we can find the best fit results, and we found that the values of G and K correspond very well with literature values. Here we have our results for gold, for copper, and we found that in the case of copper, KQ had a negligible impact on the quality of the fit. And this is because the equilibration process is largely dominated by electron-photon coupling. Nonetheless, we still have good agreement with literature values for the electron-photon coupling. Lastly, I'd like to talk about the spectral response of the change in electron temperature over the visible spectrum. And what we found is that we have qualitative agreement of the change in electron temperature over the visible spectrum. As we go to lower wavelengths, we do see an increase in the change in electron temperature due to a decrease in the optical penetration depth of the pump into the material. However, we do find discrepancies which we believe are due to the change in density of states, which we have yet to incorporate into our model. So in conclusion, we measured the equilibration process of thermal electrons in gold and copper using our visible pump, visible probe spectrometer. We've confirmed our hypothesis that the electron decay rate is dependent solely on the peak change in electron temperature and not directly to the photon energy. We found that the two-temperature model is a viable tool to get accurate estimates of the electron-photon coupling G and the thermal diffusivity K and Q. We found qualitative agreements with our model and the change in electron temperature over the visible spectrum. However, we found that the two-temperature model still needs to be improved by accounting for changes in the density of states. So what we'd like to do in future work is to incorporate the density of states into our two-temperature model in an attempt to match spectral data with simulations. We'd like to study our samples over a larger spectral range, particularly the infrared region, 700 to 1,000 nanometers. And once we get strong agreement with simulation and noble metals, we'd like to move on to studying quantum materials, such as insulating cuprates and magnetic materials. Thank you, and is there any questions?
Yeah, it's a very nice talk. Now, in your model, there's no direct energy transfer to the lattice.
Sorry?
In the model, there's no direct, there's no direct energy transfer to the lattice.
Yeah, that's
Why is that?
That's an assumption that we've made, and I believe it's because the electrons are shielding the lattice and absorb most of the energy of the chain. Very little energy is transferred directly to the lattice.
This might be a very stupid question, but your golden copper salts, you had a slide, hope you talked about that. With your two-temperature model, when I look at that data, that seems like a very linear behavior, whereas your model, which I assume is a numerical solution to those very complicated equations, show some fluctuations. Wouldn't there be a more simple way to actually model that to be purely linear?
So you're saying the two-temperature model is not completely linear. There's
Yeah.
Yes, we think that this is just small differences when fitting to the data. There are actually many data points which we're applying exponential fits to, and there is not because of the 1 picosecond thermalization time, which ranges from about 0.6 picoseconds to maybe 1 picosecond, depending on the total power. We have to adjust the starting points of the fits, and that is being it's being something that we're looking into to remedy. But the small changes are most likely due to where we start our